Welcome back from spring break. I hope you guys all had a good week off. We're going to jump right back in, starting with Unit 6, which is learning about the world, which is really starting with Chapter 23, which is inferences about means. And inference means confidence intervals and hypothesis tests. So we're really doing the same thing, just slightly different. We're going to start by talking about Gosset and Gosset's tea. Gosset's a person, and he had a really sweet job. He was the quality control engineer for the Guinness brewery. It was his job to make sure that each stout that left was quality. He ended up rejecting a lot of batches that were in fact good, about 10% more than he thought. So he thought he was rejecting 10% more than he needed to, but again, he wanted to make sure that every beer that left was a quality beer. Because he was so dedicated to his job, he decided that he would take time off to research the problem that he was having, and he found out that the problem was with his standard error, which is the standard deviation divided by the square root of n. This was causing his sampling model to change. So for every sample, his model ended up changing, so he couldn't keep using the normal model. What happened is that he knew that he needed a new model, and therefore he called it a t-distribution, which is why we're saying it's Gosset's t, because it's a t-distribution, and he kind of named it after himself. However, Guinness didn't want him to publish his findings, and made Gosset use a pseudonym. So even though he called it was originally going to be Gosset's t model, he ended up calling himself Student, and as a result, the model he found is actually called the student's t-distribution, or the student's t model. His model is always bell-shaped, much like the normal model, but the details change with different sample sizes. So if your sample size is 30, that's going to be a different model than if your sample size is 20. So the student's t models form a whole family of related distributions because they are all unimodal and symmetric. They're all bell-shaped, but each sample size will produce a different model, so it becomes just a family of related distributions depending on a parameter which is known as degrees of freedom. The degrees of freedom is going to be denoted df, and the model would be t and then a subscript df, where df will be a number. So like t sub 8 means that you have 8 degrees of freedom. So what does this mean for means? To make confidence intervals or hypothesis tests for a mean, we have to use Gosset's model. So we have to use a t-distribution. For means, the right values for the degrees of freedom is n minus 1. So it's your sample size minus 1, or 1 less than your sample size. So if you had a sample size of 10, your degrees of freedom would be 9. Looking at a practical sampling distribution model for means, when conditions are met, the standardized mean, and by standardized mean, it's kind of like a z-score, only because we're not using the normal model, we're really going to call it a t-score. And that is t equals your sample mean, which is our y bar right here. That's our sample mean that we get from our sample, minus mu, so this would be the known parameter, so we would get that from our null hypothesis, divided by the standard error, where your standard error is the standard deviation of your sample divided by the square root of n. And we should have seen that standard error before. With the t model, the margin of error gets bigger. So it's slightly different from the normal model, and because of that, it causes our margin of error to be slightly bigger. Not crazy huge, but a little bit bigger than we might expect. That also means then that for means, your confidence intervals tend to be a little bit wider than they would be for proportions. And your p-values will be bigger. So again, with confidence intervals, we're still going to need a margin of error. To do hypothesis tests, we still have to calculate a p-value. The p-value still means the exact same thing. It's still the probability of our observed statistic occurring, given our null hypothesis is true. But for means, our p-values will end up being a little bit bigger than they were for proportions. However, we are not going to end up changing our alpha levels. So our alpha levels will still stay at 1, 5, and 10%. The student's t models are unimodal, symmetric, and bell-shaped. They are not much different from the normal model. But the tails are fatter. However, when n goes to infinity, so when your sample size is infinitely large, the t model is the normal model. There is no difference. Now, having an infinite number of samples is completely unreasonable. Can't happen. However, when n gets to be more than a few hundred, you can hardly tell the difference. So if you have a very large sample size, so if you have a sample size of 200, you can go ahead and use the normal model. You don't have to worry about the t model. So the student's t versus normal distribution. Okay, so here's a graph that really kind of shows it. So the black dashed line, that's your normal model. That's what we've been using until now. The other lines are the student's t distribution with different degrees of freedom. So the red line right here is a degree of freedom of 30. So 30 degrees of freedom. And note how close that actually is to the normal model. And that's only a degrees of freedom of 30. So when you get to a degree of freedom of 100, you're almost exactly the same thing. When we lower our degrees of freedom to 10, which is our blue line, we're a little bit shorter, and if we come down here, our tails are a little bit fatter. If we go even lower to a degree of freedom of 5, again, we're still lower at the peak, and again, our tails are still a little fatter. The green line is a degree of freedom of 2, and the purple line is a degree of freedom of 1, which really lowers the peak and really makes your tails quite large. So this is why it's called a family, because all of these follow the same concept. However, they are all slightly different based on the sample size. And again, one more time, when your sample size gets much larger, a couple hundred, or even I'd say 100, the differences between the student's t distribution and the standard normal distribution is it's very small, so you can almost interchange them. So finding t values. So just like before when we had z-scores and we used our z-score for critical values, we now have to use a critical value but for t values. So there is a table T in the back of the book that has t values. And I'm actually going to show us how to use that in class tomorrow. We also can use our calculator, and I will also show us how to do it on our calculator. Because in some cases, it'll be almost easier to use the table, and in other cases, it's going to be easier to use the calculator. For a one sample t interval, the interval is going to be your sample mean plus or minus your margin of error. So all of this right here is your margin of error, which is your critical value times your standard error. But our critical value is not a z asterisk anymore, it's now a t asterisk, where we have our degrees of freedom is one less than our sample size. And we'll have to use that table, the t table, or our calculator to be able to figure out what this value should be. And then a one sample t-test, which is for a mean, is a hypothesis test that's exactly the same, except our standard deviation. And same thing for our standard error here. It ends up being the standard deviation of your sample, which can either be calculated or will be given to you, divided by the square root of n. Again, this is not any different really than what we did in the previous unit. The only difference really is the critical value, the t's, and calculating it based, your p-value based off of a t instead of a z. Which brings us to our assumptions and conditions. They are pretty much the same. You still need to be random and independent. You still need to have less than 10% of the population. But the one difference is that we no longer are checking our success-fail condition. We are now checking the nearly normal condition. The nearly normal condition means that the histogram should be unimodal and symmetric. If you have the data, you have to actually check this. And by checking it, I mean you're going to actually show a histogram. You can go ahead and calculate it on your calculator and just sketch it based off of that. It does not have to be perfect, but it does have to be shown if you have the data. If you don't have the data and they just are giving you the statistics, then you have a little more leeway and you can kind of just state that there's no reason to believe that it wouldn't be normal, but we have to make sure that it is nearly normal. So again, the assumptions and conditions, random and less than 10% of the population are the same as before, but instead of the success-fail, it now has to be nearly normal. That is it for tonight. Tomorrow in class, I'm going to show you how to find your t-values using the back of the book and your calculator, and then we're going to run through a couple of examples together in class tomorrow. But I hope you guys all have a great day or night, and I will see you tomorrow.